So welcome to the second lecture on Sudoku in Haskell. What we're going to be doing today is we're going to kick things off with a brief review of what we did last day, and then we're going to be writing our first Sudoku solvers. So let's start by refreshing ourselves about what the rules of the game are. So here is a Sudoku grid. It's got rows, columns and boxes, and some numbers are filled in and some numbers are not. And the name of the game is you've got to fill in all the blanks such that each row, each column and each of the 3x3 boxes in red has each of the numbers 1 to 9 exactly once. So no duplicates and no blanks. So what we did last day is we defined a bunch of new type declarations, and we defined some simple functions which we're going to be using today. So I want to start by reviewing these as well. So here's the basic definitions for types which we had. So we said a Sudoku grid is going to be a matrix of values, and then a matrix of things is going to be a list of row of things. A row of things is simply going to be a list of things, and then a value is going to be a character. And as we mentioned last day, essentially a Sudoku grid is basically a list of characters, but having some of these intermediate data types, in particular the parameterized type for matrices and the parameterized type for rows, is going to be useful to us today. So that's our basic data type declarations. Then last day we also defined some simple functions as well. So we defined 3 functions called rows, columns and boxes, and each of these simply takes a matrix of things and pulls out the corresponding entries as rows. So for example, the columns function takes a matrix of things and pulls out each column as a row. And as we saw last day, that was just defined by simple matrix transposition. Now what we ended up with last day is we defined a simple function called valid, which checks to see if a Sudoku grid is valid. And validity here simply means that there's no duplicates in any row, any column or any box. So for example, the number 2 doesn't occur twice in a single row or a single column or a single box. And also what we looked at last day, which maybe seemed a bit kind of strange and trivial last day, but we'll see why they're actually useful today, is 3 properties of these simple functions, rows, columns and boxes. And the properties are that if you apply the rows function twice, you get back where you started. Similarly, if you apply the columns function twice, you get back where you started. And if you apply the boxes function twice, you also get back where you started. And again, these may seem like trivial little properties, but we'll see that they're actually very useful today when we come to implement our first Sudoku solver. So let's actually implement our first Sudoku solver now, and I'm going to call this a basic solver. So we're going to implement a basic Sudoku solver. And the way this is going to work is we're going to give our solver a Sudoku grid as input. So that may be a partially filled in grid like the easy grid which we saw last day and on the cover page today. And then what we're going to give back is we're going to give back a list of all possible grids that solve the problem. And actually you can see here we're solving a more general problem than the one we actually want to solve. Each Sudoku grid that appears in the newspaper only has a unique solution. So in principle, we could make the solve function take a single grid and give back the single grid that solves it. But actually, we're going to solve a harder problem here. If a grid has more than one solution, we're going to give back all of them. And this is a kind of common thing in algorithm design. Sometimes it's easier to solve a harder problem, like returning all possible solutions to a Sudoku problem, rather than giving back a single possible solution. And of course, if we wanted a single solution, we'll just take the head of that list, and under lazy evaluation, that will do the minimum amount of computation necessary to just give us one unique solution back for the puzzle. Okay, so how is our basic Sudoku solver defined? So I'm going to give you the definition, and then we will figure out how to define the parts which we haven't seen yet. So it's going to be the composition of 3 functions. So we're going to filter valid solutions in the end. After, we'd use a function called collapse. After, we apply a function called choices. Okay, so we've got a simple function composition here. We're composing three functions. In order to solve a Sudoku grid, we're going to first of all apply a function called choices, which we haven't yet defined. Then we'll pass the output of that into a function called collapse, which we haven't yet defined. And then in the end, we will filter out all the Sudoku grids which are actually valid, i.e. no duplicates in any row, any column, or any box. So this is a simple one-line function definition using function composition. If you're not so familiar with function composition yet, I can write it as a more regular Haskell program. I could say if you want to solve a Sudoku grid, you filter valid, and then you apply collapse beforehand, and then you apply choices beforehand. Okay, so what you can see here is we're taking the Sudoku grid G in, we're applying the choices function, then applying the collapses function, and then filtering the valid things out. And this is exactly the same as the one-line definition which we have here, but I prefer the one-line definition because we haven't needed to name the argument G, and we've got rid of all the brackets. And it really expresses the intuition that solve is just a composition, or a pipeline if you like, of three different functions altogether. Okay, so let me just get rid of this one. So what we need to do now is think, how can we define the two parts of this definition that we haven't seen yet? How do we define choices and how do we define collapse? So this is what we're going to do now. So first of all, we're going to apply the idea of making choices. And the idea here is a very simple one. What the choices function is going to do is it's going to take each blank cell in a Sudoku grid and replace it by all possible choices between 1 and 9. So let me explain what this means with a simple picture. So let's draw the top left-hand corner of the easy Sudoku grid, which you've been working with. So there's the kind of corner 9 squares here. And we had a 2 in here, and we had a 7 in here, and these values were given to us. And then what the choices function is going to do is take an initial choice matrix, or an initial Sudoku grid like this one, and it's going to replace each of the blank cells by all possible values 1 to 9. So in this cell we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9. And similarly in this cell we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9. I should have chosen a slightly smaller pen size here. So on here, similarly for each of these boxes, just fill them all in. Each of the blank cells is going to get the number 1 to 9. And notice that we don't make any effort at this point to try and be clever. Because, for example, we have the value 2 sitting here, so there's no point in having any 2's in anywhere else in the row, or anywhere else in the column, or in fact anywhere else in that top 3 by 3 box. But we're not trying to be clever here. We'll do that later on. The choices function just simply replaces each blank cell by all the possible numbers between 1 and 9. No attempt to be clever at all at this point. So let's define the choices function now. So what choices is going to do is, well, first of all, we're going to define a little type for what choices are. So choices with a capital C is going to be a list of values, like 1 to 9. And then the choices function is going to take an initial Sudoku grid, such as the easy grid, which we've been working with. And then what it's going to give us back is a matrix of possible choices for each cell. And now you see why the matrix type is parameterized, because, oops, that's the wrong thing. Because here we're having a matrix of choices. We're no longer just having a matrix of values, which are single characters. Now we're having a matrix whose entries are lists of values, or all possible choices. So we see now the advantage of having this parameterized data type for matrices. So we can define the choices function now. This is a very easy one to define. If you give me a Sudoku grid, what I'm going to do is a double map. So let me write this down and then explain how it works. So what I'm going to do is I'm going to map the map of a choice function across the Sudoku grid. And the choice function I'm going to define in a little where clause here. And it's going to be a small local function which simply replaces each blank cell in a Sudoku grid by all the numbers 1 to 9. So this is a very easy function to define. If you give me a value, v, which is a character, I test, is the value a blank, which is a dot? If it is, I'm going to replace it, or return, rather, the list 1 up to 9. Otherwise, I'm going to just put the little value in a list. And I have to do this because I'm returning a matrix of choices. And all the map here is doing is I've got a double map here. The double map is simply applying the choices function to every cell in a grid. And if you don't understand how the double map works, think about the types, maybe draw a little picture, and everything should become clear, hopefully. So that's the choices function now. The next function we need to define is collapse, which is sitting in the middle here. So what does collapse do? So let's have a think, first of all, about the type of collapse. So what collapse is going to do, if you work out its type, which you can work out just by looking at the components which surround it, it's going to take a matrix whose elements are lists of choices, and what it's going to give you back is a list of matrices. Okay, so it's going to take a matrix of lists and give you back a list of matrices. And you can then think, well, what does this function actually do? Well, what it's going to do is it's going to collapse a matrix of choices to a choice of matrices by producing all possible combinations of choices for each cell. And that's a bit of a mouthful, but the idea is actually very simple. So let me explain this again with a picture. So let's have the top left-hand corner of our easy Sudoku grid. And what we have is we have the value 2 sitting there in the top left-hand corner. And then when we applied the choices function, it will have a 1, 2, 3, 4, 5, 6, 7, 8, 9 sitting in that blank cell there. And it will replace that blank cell sitting next to it. Similarly, you get 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's what the choices function would do. And now what collapse is going to do is for each of these cells where there is a choice to be made, so there's 2 cells with choices to be made, it's going to consider all possible combinations of choices. So for example, out of this function, we could have this choice. So the 2 is already fixed. We could pick a 1 for the second cell and a 1 for the third cell. Or we could do something different. We could pick a 2 here, that's already fixed. We could keep the 1 here, we could pick a 2 here. Or similarly, we could have 2, 1, 3, and so on. And we could have kind of 9 possible choices for the third cell there. And then we could go down and say, well, what about the second square? Well, the first cell is still fixed. The second one could then click over to 2, and then you could have a 1 here, and then so on and so on. So you can see here that in this case, if we just applied collapse to this little part of the choice matrix, then you would actually end up with 9 squared things coming out, so 81. So really, I don't think collapse is actually the right name for this function. Maybe I should have called it explode, because it's actually going to explode a matrix of choices into a choice of matrices. So that's basically what the collapse function is going to do. It's going to take a matrix where the entries are lists, and then it's going to consider all possible combinations of choices that you could make for each of those cells. So in order to define this function called collapse, what we're going to do is first of all define a function that produces all possible combinations of elements from a list of lists. So let's think about how to define this first of all. So I'm going to define a function called CP. And I'll explain in a moment why I've called it CP. And what CP is going to do is it's going to take a list of lists and it's going to choose all possible ways of choosing one value from each list. So I've got 3 lists here. I've got a 1 and a 2, and then a 3 and a 4, and then a 5 and a 6. So I could choose the 1 from the first list, the 3 from the second list and the 5 from the third list. That'd be one possible way of choosing a value from each list. Or I could choose a 1 from the first list, a 3 from the second list, and a 6 from the last list. Or I could choose, for example, a 1 from the first list, a 4 from the second list, and a 5 from the third list, and so on and so on. So what this function is doing is it's taking a list of lists, in this case 1, 2, 3, 4, 5, 6, and it's choosing all possible ways of choosing one value from each list. So I could choose a 1, a 3, and a 5, a 1, a 3, and a 6, and so on and so on. And I've called this function CP because it's essentially computing the Cartesian product of a list of lists. You may remember from your mathematics courses in the first year, if you write A times B, where A and B are sets, that's going to be the set of all pairs AB such that A is an element of A and B is an element of B. And that's called the Cartesian product of sets because it's taking two sets, A and B, and giving you all possible ways of choosing one element from the first set and one element from the second set. And the CP function does essentially the same thing, but it's working with lists rather than sets. So then we can think, well, how do we actually define this CP function? And it's very straightforward to define. So define CP. It takes a list of lists of A things, and it's going to give you back the same, a list of A things. And it's got a simple base case. If you give me a list with nothing in it, I'm going to give you back a list with the empty list in it. And I'll come back to this in a minute because it's an important point for the base case. And if you apply CP to a non-empty list of lists, so you've got a pattern here. You have X's is the first list, like the 1, 2. X's is everything else, like all of that. Then you think, well, what am I actually going to do? Well, we can define this using a simple list comprehension. We're going to compute the list of all lists, Y followed by Y's, such that Y is an element of the first list. So this is going to choose, this generator here, is going to choose all possible values Y coming from the first list. And then what we're going to do is recursively choose all possible lists Y's from CP of X's. And that's all possible ways of recursively processing the tail. And then we will package these two values up together as a list. Okay, and again, you might need to think a bit and maybe try and reconstruct this definition for yourself to see why this achieves the desired behavior. Now we can come back to the base case. You might think, well, why in the base case did I return a list with the empty list in it? Why didn't I just write the empty list here? And the answer is, and you can check this out for yourself, if I just return the empty list here, this would make this function always return the empty list. Okay, and you can try and figure out why that is the case, but you can try it out practically as well, just to see that you actually do need to return a list with the empty list in it as the base case. Okay, so now we can use the CP function, our Cartesian product function, to actually define what it means to collapse a choice matrix. So I'm defining the function called collapse now, and it takes a matrix of choices, so a list of possible things that each cell could be, and what we're going to get back is a list of all possible matrices that we get by choosing one thing for each cell. And it's a very simple one-line definition now. So if I give you a choice matrix M, what I'm going to do is apply the CP function in a certain way. What I'm going to do is internally, I'm going to map CP across each row of the matrix. And that's going to collapse each row. Okay, so this part here is going to collapse each row. And then what I'm going to do at the outer level is apply CP once more, and this will collapse each column. So this is going to collapse each column. And again, you may need to stare at this bit, maybe experiment with it, and maybe even try and rewrite it yourself to convince yourself that this actually does the right thing. So now, actually, in a very short amount of code, we actually now have our working Sudoku solver, our first working Sudoku solver. So if we go back to here, quite a few slides back, here is our Sudoku solver. What it's going to do is you give it a Sudoku grid. It's going to apply the choices function first of all, and that will replace each cell by all possible choices 1 to 9. Then you're going to apply the collapse function, and that will consider each possible value that you could have in each cell by considering all possible combinations of those values. And then finally, we're going to filter out the resulting grids which are valid. So they satisfy the basic rules of the game, that there's no duplicates in any row or any column or any box. So this is essentially a one-line program that solves Sudoku puzzles. But there's a little problem, and the problem is a practical one. So if you go to the web page for the module and you download the Sudoku code and you load it into GHCI and you start it up and you say solve the easy grid, it's just going to sit there. It will never terminate, basically, not in your lifetime anyway. And in principle, this Sudoku solver works, but in practice it doesn't. And in practice it doesn't because the search space in this case is too big. If we go back to our grid, right back at the start here, if you count the number of blank squares here, there's actually 51 blank cells in this grid. So if you think what the collapse function is going to do, out of this function here is going to come 9 to the power of 51 grids. Because for each of those empty cells, there's going to be 9 possible things that it could be, and collapse will consider all of those, so you're actually going to get 9 to the power 51 grids coming out here, and that's a number which has approximately 49 digits in it. Okay, so you can try that out for yourself. What is 9 to the 51? It's a 49-digit number, roughly. That's not going to terminate in anybody's lifetime. So in principle, this Sudoku solver works, but in practice, it doesn't. So we need to think a little bit more carefully. What we're going to do then is think about trying to prune the search space down. So we're going to think about pruning the search space. And the way we're going to do this is very simple and very obvious. So when we considered the top left-hand corner of our easy Sudoku grid, which I'll draw again here, we had a 2 here and a 7 here. And when we applied the choices function, it just blindly replaced every single blank cell by all possible numbers between 1 and 9. But that's nonsensical because, for example, in the first row, we have this number 2, and down here we have a number 7. So what this tells us is nowhere else in this row should we ever have a 2, because that would invalidate the rule of the game. Nowhere else in this column should we have another 2, because that would invalidate the rule of the game. And in fact, nowhere else in this 3x3 box at the top left-hand corner should we have a 2. So there was no point in considering a 2 anywhere there. And it's the same with a 7. There's no point in considering a 7 anywhere in the row or the column with the 7 in it or the 3x3 box with the 7 in it. So the idea here is that we can prune out any choice that occurs as a single entry in the corresponding row, column, or box. Okay? So what we're going to do then is we're going to write a simple function called prune, and let's think about the type of it first. So what prune is going to do is it's going to take a matrix of choices and it's going to give us back a matrix of choices, and it's going to prune out any choice that occurs as a single entry in the corresponding row, column, or box. So how am I going to define this? So this is going to be another one of our one-liners. So we're going to assume, or we're going to define actually, a helper function called prune by. And what prune by is going to do is allow us to prune by the boxes, the columns, and the rows separately. So what we're going to do is we're going to have a simple function composition. We're going to prune by the boxes after pruning by the columns, after pruning by the rows. So this is going to prune out, if we consider this part, for example, this is going to prune out any value which occurs as a single entry in the corresponding row. Then we'll prune out any value which occurs as a single entry in the corresponding column, and then we'll prune out any value that occurs as a single entry in the corresponding box. So we're going to prune the rows, columns, and the boxes. And the prune by function is a clever little helper function. And what prune by is going to do is you give it one of these functions, rows, columns, or boxes, and what it's going to do is a simple function composition. And this is the clever part. So what prune by is going to do is you give it a function f, which will be one of rows, columns, or boxes, and then it's going to be a simple function composition. And what the function composition is going to do is imagine f was the columns function. Okay, so we'd apply the columns function. That would extract the columns as rows, and then what we would do for each of those rows, we'd apply a function called reduce, which we haven't yet written, and then we'll put the columns back together. And here we're exploiting the fact that when you apply for example, the columns function twice, it gets you back where you started. So this is letting us prune the columns by transforming the columns into rows, operating on those rows, and then putting the columns back together. And it's the same for the boxes and the rows as well. Okay, so this is a clever little function which is exploiting the fact that we can turn boxes into rows, for example, operate on those rows, and then turn them back into boxes. So we don't need to write a separate pruning function for columns and rows and boxes. We just write one function and we're done. So now we can think, well, what does this little magic helper function called reduce actually do? Well, reduce is very simple. Let's think about its type. What reduce is going to do is you give it a row of choices, and it's going to give you back a row of choices where any single entries have been pruned out of the corresponding other choices. Okay, so again, that's a little bit of a mouthful. What does this actually mean in practice? Well, what it means is if you give me a row of choices, so suppose the first cell had the choices 1, 2, 3, 4, and the second cell had no choice, it was just a 1, and the third was a 3 and a 4, that's the two possible choices there, and the fourth was no choice, you have a 3. What reduce will do is it will look for any entries in this row of choices which are single. So here we've got a single 1 and a single 3. And because we've already made the choice that this must be a 1 and this must be a 3, there's no point in considering the 1 here or which other one, or the 3 here, okay, and the 3 here as well. Okay, so we could eliminate those 1s and 3s from the other entries. So what we should get back then is if we eliminate or reduce, we should get 2, 4. So the 1 and the 3 have disappeared because these occurred as single entries elsewhere. We get the 1 here, then we get a 4 here because the 3 disappears because it's a single entry elsewhere, and we get a 3. Okay, so what the reduce function is doing is eliminating choices which have no possibility to ever succeed. So again, for example, there's no point in considering this choice 1 here because we already have a 1 here, and there's no point in considering this 3 or that 3 because we already have a 3 here. So we eliminate these and we get down to the 2, 4 here and the 4 here. So I'll leave it as an exercise for you to try and define the reduce function. Again, I mentioned right back at the start of the course, if you want to do very well with the advanced functional programming course, I'm going to be setting you some exercises from time to time. And this is one of the exercises. Try and define the reduce function for yourself without looking at the notes. And it's quite an interesting exercise to do that. There's lots of different ways you could do it. Okay, so we've got the idea of pruning now. Now we can define a new Sudoku solver. So let me define our second Sudoku solver. I'll call it solve2, and it's going to be defined very similarly to before. It's going to be filter valid after collapse, after prune, after choices. So it's a big function composition again, except what we've done now is we've introduced our pruning helper function here between the choices function and the collapse function. And this will eliminate any choices which are silly or not going to ever lead to a solution because they occur as a single entry in the corresponding row, column, or box. For example, if we see a 2 in a particular row, we can eliminate that in the rest of the row, the rest of the corresponding column, and the rest of the corresponding box. So we can ask ourselves, does this make our Sudoku solver any better? And the answer is it does make it a bit better. For the easy grid, it leaves on average about 2.4 choices per square or per cell, but this still leaves a very large number of grids coming out from the collapse function. Previously, for the easy grid, we had 9 to the power 51, which I think was a 48-digit number or something like that. The number coming out of here is approximately 10 to the 24 grids coming out of here now. So it's reduced it. It used to be 9 to the power 51. We've reduced it to 10 to the power 24, but it's still an astronomical number and actually not feasible for solving Sudoku puzzles. So again, you can try this out for yourself. Try starting up GHC. So start up GHCI, say solve to the easy grid, and it's just going to sit there forever, because it's trying to explore the search space up here of around 10 to the 24 possible grids coming out of the collapse function. So we need to think a bit more deeply. The solution is quite a simple one. It's the idea that we can repeatedly prune, because once we eliminate entries which occur as single entries somewhere in the grid, those choices are not particularly, they're never going to lead to a solution. It may be the case that there's now new single entries which we can then prune again. Okay, so this is going to lead us to a new function or a new idea of repeatedly pruning. So if I take the reduce function and I apply it to the output which we got from applying it previously. So once we reduced once with this particular example, we eliminated some values and we got down to a 2 and a 4 and a 1 and a 4 and a 3. But in doing so, now we have the fact that this one here must be a 4. Previously, I think we had a choice of a 3 and a 4 there. Now we've only got a choice of a 4. So if we reduced again, maybe we can do better. And in fact, we can do better because we see that we have a 4 here. So if we reduce, that's going to give us a slightly smaller choice list. So we'll get 2, 1, 4, and 3. Okay, so this is taking the output from the previous example, which was this one here, and then if we reduce again, we manage to eliminate another choice here. So this leads us to the idea of iterating the pruning process. We can kind of keep iterating this idea of eliminating single choices from anywhere else in the grid until nothing changes. And what that means is we've reached a so-called fixed point. Okay, so let's see how we can implement this. So here is our final Sudoku solver, which we're going to define today. And what we're going to do is we're going to do the same as before. We're going to filter out the valid grids after collapsing, after fix of prune. So fix is a new function that we haven't defined yet. And then we're going to apply choices. So the only change this time is that we're now, rather than applying the pruning function once, we're going to keep iterating it until the choice matrix doesn't change. And this means finding a fixed point of a function. A fixed point of a function is a value that when you apply the function to it, you get the same thing back again. So what fix is going to do is keep iterating the pruning function until it doesn't have any effect anymore, until when you give it a choice matrix, you get exactly the same choice matrix back again. So let me define the fixed point function. So fix is going to take something which supports equality, because we need to check if two things are equal. We need to check if the output, once we apply pruning, is the same as the input. So we need an equality constraint on here. Then we're going to take the function we're going to take the fixed point of. So that's the thing we want to iterate until we don't get a change. Then we take an input and it's going to give us an output. Okay, so the type's a bit weird, but the basic idea is very simple. We're going to take a function as an input here, And we're going to take an input to the function, and we're going to iterate the function as many times as possible until the output is the same as the input, and then we'll give back the result. Okay, so how does this work in practice? Well, what fix is going to do is you give it a function like prune, you give it an argument, and that will be, in our case, a choice matrix. And what it's going to do is, we're going to do a little equality test here. So let me just write down the definition, and then I'll explain, how it works. So the definition is very simple. We're taking a function f that we want to iterate until it doesn't change. We're taking an input to that function, and then what we're going to do is apply the function once, first of all. So we apply the function f, and we get a new output x prime. If the output and the input are the same, that means we have found the fixed point of the function. It doesn't change anymore, and we simply give back the result. Otherwise, we're going to call ourselves with the new output and keep iterating. So what this is going to do is keep iterating, in our case, the pruning function, until it just doesn't change the choice matrix. And you can try this one out on GHCI. If you start up GHCI and you say solve 3, the easy grid, it will give you a solution instantly. So it'll give you an instant solution, which is very satisfying. And in fact, it will solve any easy grid, not just the particular one which I've given you. It will solve any easy puzzle from the newspapers instantly. But there's a problem. Not every Sudoku puzzle is an easy one according to the rankings. There's other levels of rankings as gentle and difficult and diabolical and impossible and so on. And if you look in the source code, I've given you some other example Sudoku grids, and I've given you, for example, a gentle grid, which is a little bit harder to solve. And if you try solving with the third Sudoku solver, the gentle grid, it won't terminate anymore. And in fact, for the gentle grid, it'll end up exploring about 10 to the 29 grids again. And in fact, that's what you'll have coming out of here. For the gentle grid, you'll have about 10 to the 29 grids coming out. So it doesn't actually work in this case. So that's it for today. What we've done is we've defined our first few Sudoku solvers. Our initial one in principle worked, but was too inefficient to be tractable. It was considering too many grids to actually ever give a solution. Then we introduced the idea of pruning the search space, which helped us a little bit, but still couldn't solve any puzzles. Then we introduced finally the idea of iterating, the idea of pruning the search space using this fixed point function. And that let us solve easy grids, in fact, any easy grid from the newspaper. But if we try it with a gentle grid, it won't work. So we'll need to think a bit more deeply next time. So that's it for today. I'll see you again next time.